SwayamPrabha. Digital India. Educated India.
Hello everybody, we will continue our lectures on optimal control of distributed parameter systems. As I told in the last class, we will see some SNEC ideas getting embedded into optimal control of DPS, distributed parameter systems. This is what we will largely talk here, both in the framework of without model reduction and with model reduction actually. Alright, so largely the topics that I will carry for model reduction will talk about these two publications for sometime back it happened 2003 and 2008 like that actually, and then there are other ideas also 2001 things like that too actually. Anyway, so these the more details you can find in some of these references actually. Alright, so a little bit very brief review of optimal control through single network adaptive critique. I mean we have taken a lecture there. One full lecture is there for adaptive critique where you can see details on that, but just a little bit recapitulation of what it is. So, first thing is optimal control formulation in general has several advantages. Linear assumptions of system dynamics or aerodynamics is not necessary either. Okay, so it avoids typically high control magnitudes normally. Okay, the system dynamics is accounted for in planning the trajectory, and hence your control normally does not become very high at some point of time. Okay. And then system need not be okay. Now coming back to this topic, what happens typically is if the system error is large, if you go for stability sort of control theory, then the control magnitude will become also large, okay, like PID control or dynamic inversion like that actually. But if you have optimal control in hand, it will tell okay there is time, it is not talking about momentary sort of behavior, talks over a behavior over a period of time and all that, and that is philosophical reason why it happens to be a better distribution of control magnitude over a period of time, accounting for the system dynamics actually. Okay, so that is one advantage of optimal control theory. The other one is system need not be square. Okay, that means you do not have to have number of controls need not be equal to number of states or outputs. The third one is feedback form of control solution is very difficult. These are good things, but this is actually a very bad thing because feedback form of control solution typically happens to be quite difficult actually. Okay, so now coming to the review of a little bit discrete time domain optimal control theory, especially coming through this approximate dynamic programming sort of ideas. This is finally the thing. You have state equation, you have co-state equation, you have optimal control equation. Typically state equation develops forward, co-state equation develops backward, and these two are dynamic equation. This is static equation like that actually. Okay, so all these things we know, and remember UK is a function of xk, but lambda k plus 1. This is the discrete time optimal control theory actually. Now coming to this single network adaptive critique ideas, we have to synthesize a set of neural networks in such a way that given an xk information, we should be able to find what is our lambda k plus 1 information actually. Okay, so that is what the single network adaptive critique synthesis is all about actually. An assumption here is optimal control equation is explicitly or symbolically solvable for control and for control in terms of state and co-state actually. The advantages obviously it retains all the advantages of adaptive critique, again it eliminates the action network from the training process and also eliminate the iterative training between action and critique. This is what happens. This is a little bit comparison with respect to adaptive critique versus single network adaptive critique. We have talked in detail in one of the previous lectures actually. Okay. Then the whole idea here single network adaptive critique is something like this. We have this xk, you have a critique network, you have to get lambda k plus 1, but obviously to begin with this is non-optimal. So, you have to get something like optimal lambda k plus 1 with respect to this xk. So, that knowing this xk and lambda k plus 1, you can use that in optimal control equation and get uk. So, initially this is non-optimal, but still you can use that these two and get your uk. Then get the xk and uk are known, hence you get xk plus 1, again you use the same critique network, get lambda k plus 2, then using these two you get lambda star k plus 1. So, taking this as input and that is desired output, you train this network and stop when these two are kind of close to each other. That is what we have discussed in detail before. Now, advantages of single network adaptive critic, it retains all good features of adaptive critic, it eliminates the action network and hence eliminates the approximation error due to action network. There is no necessity of iterative training also between action and critic networks. Turns out to be much simpler than the neural network architecture, much simpler neural network architecture for synthesis of optimal control for this class of problems actually. Okay. So, it leads to some sort of significant amount of computational savings, especially when you talk about distributed parameter system synthesis actually. Okay. But limitation again is applicable only when the optimal control equation is explicitly solvable in terms of other two variables. Now, how to extend these ideas to distributed parameter system? And here this finite difference method comes very handy. Okay, we are not bothered about model reduction and things like that. We just blindly put the grid points and try to get some solutions out of it actually. So, let us see what the program we are talking about. We are having system dynamics of this form, xk plus 1 is something like this. These are all discretized at node points. K represents the evolution of time, whereas j represents the grid points in space. Okay. So, you have any grid point location j. Okay. This system dynamics is a function of all other node points state values and the control applied at that particular point actually. Okay. So, this again actually whether it is all node points or limited to one or two node points, it again depends on the order of the system dynamics in spatial derivative. If you have second derivative like the example that we discussed last time, then probably it is a function of neighboring nodes actually. If you have a fourth order derivative, there suppose del square x by del fourth x by del y fourth like that, then it may repercolate. The repercussion can go to little more grid points in both sides actually. So, like that actually depending on the system dynamics. In general, you can think that at any node point, the system dynamics behavior is a function of states at all other node points and control applied at that particular node point actually at that particular time also. The cost function to optimize is given in this form, everything is in discrete domain. So, first thing is something like a summation over space, the next thing is a summation over time, a double integral sort of thing what we saw in the continuous time domain. Now, going to the same idea of approximate dynamic programming sort of thing, you can whatever is jk, k starts from, so here it will k tilde starts from k to n minus 1, that is cost to go from time to from k. It can be split into the two parts. It is first is utility function at time tk and then jk plus 1, that is cost to go from k plus 1. It is like dynamic programming sort of ideas actually. Okay. Then there is a definition of lambda and the definition turns out to be like this. We define lambda at grid point j at time instant k, that is lambda kj in this form, lambda kj times delta y happens to be like this actually. Okay, this is a kind of compatible definition in the distributed parameters settings basically. Remember in continuous time lambda happens to be del j by del x actually, that is we know that, but blindly we can't put it here, we have to be slightly more careful here. Tell that okay, lambda kj is this one divided by delta y or this times delta y is equal to that actually. So, that is the definition of lambda here. Then co-state equation is a convoluted process, you have to really do a lot of bookkeeping to get it there, but it can be done. Okay, do not get afraid to see this algebra and all that actually. Term by term you can do, especially when you have really understood the derivation with respect to the lumped parameter system in some one of our previous lectures. You can start similar things, okay, utility function, then cost to go, then see what terms is what is the dependence on other thing. Do not forget the summation over spatial domain and things like that. Carry out the algebra again term by term, let me not explain too much here, but is there in the paper, it is there in the slide also here. So, carry out the algebra, you will finally end up with some expression like this. Then optimal control equation also you can do algebra and then this should be equal to 0. Then go back to that and tell okay, if this expression happens to be 0, okay, then what is the simplification that I can get here. Okay. So, obviously, this term what you see here happens to be 0, okay, last term. So, you will end up with only this term actually. So, this summarizes this behavior, that you have optimal control equation and in general co-state equation is given like this, whereas on the optimal path this co-state equation can be simplified to something like this. Okay. So, you essentially deal with this equation as optimal control equation, and this equation is something like co-state on optimal path actually. Okay. And the single network adaptive critic for DPS distributed parameter system roughly remains the same, very similar structure is what you have seen before. The only difference is at the neural network structure is different, and that structure, okay, this turns out to be something like this. At neural network at node 1, node 2, node 3 and all that you see, and they are not inputs are not only xk is the value of state at time instant k, but they are also take, see for example, this network at node 2 will take input from node 1 and node 3 as well. So, the neighboring node grid point values also turns out to be an input to the same network, otherwise the networks do not converge actually. Okay. So, this is the proposition that we first proposed in around 2000, 99-2000 like that, and then resulted in the 2001 paper actually. Anyway, so the reference I will give you. Okay. So, this is this very similar structure, but the neural network details what you see as neural networks here, we have to really worry about synthesizing in this sense basically. Okay, that is the difference here. Then how do you generate let us say profiles for neural network training? That can be done in various ways, which is again necessary for this other approach, where the model reduction sort of POD approach also we need all that. Because if you talk about lumped parameter system, you know a bound from the where the system dynamics states will deviate and all that actually. So, from there you collect randomly keep on collecting a bunch of point values actually. That means, you can randomly select a large number of state values for training purpose, there is no problem actually. Okay. But if you talk about distributed parameter system, that luxury is not there. So, what we do is we have to be slightly more careful and then tell now initial conditions are profiles over spatial domain, remember that. So, because of that we have to bring in some concept like L infinity norm, or probably depending on the problem you can have some sort of energy content ideas, or in general you extend the energy content ideas and then propose something like L2 norm and all that. Remember, the state values are state profiles are needed, and state profiles cannot be discontinuous actually. Okay. State values, state profiles have to be continuous over the spatial dimension actually. Okay. So, that is what restricts us to choose that, and also a good thing, because infinite number of profiles, the more and more you become realistic, the training becomes better and better actually. So, the very first thing, if you really want to worry L infinity norm sort of thing, which is not really a very good idea in my view, but still you can do that. You can see, you can decompose these state values to various components, that x1, x2, x3, x4 are the components of the state vector. Okay. Remember, in distributed parameter sense only. Okay. And then you can see this, then you can tell, okay, my values at all these, okay, this x1k infinity norm has to be less than some value, and this x2k infinity norm has to be less than equal to some value, like that actually. Okay. And then you finally tell, okay, my SI, which is the domain of interest for me, is the direct sum of these sets actually. Okay. So, essentially you generate profiles within this SI. So, essentially the idea here is well, I mean pictorially speaking, something like this. You tell something like degree points are there, some 1, 2, 3 something like are there. Now, here tell this will like this value is bounded here, this value is bounded here, that value is bounded this much, this is this much. So, independently I will select these points, okay, within that bounds, and then I will join these points actually. Okay. This is pictorial idea of that. Okay. So, this but it is not really a very good idea in my view, because see 1, 2, 3, 4 talks about this grid point things and all that actually that way. So, we need better things better than that, because this piecewise joining is also not a very nice idea actually. Alright. So, the next idea is something like this, something like energy based, and let us say you define kinetic energy as something like integral of 0 to yf x2 square, and the potential energy is this one del x1 over del y square dy sort of thing. Okay. And this is very naturally it will come from distributed parameter system analysis actually. Okay. So, if it is like that, if the problem definition is like that and the implication is like that, then you tell, okay, at the maximum the total energy, which is nothing but kinetic energy plus potential energy, can deviate only so much actually. Okay. In other words, my entire energy content of the system is bounded by that value E naught actually. Okay. That has to be specified as a control design specification sort of thing. And if that is the case, then satisfying this condition and then these definitions, we can actually generate these smooth profiles in a good way basically. How do you do that? You can let us say you can talk about something like a function, something like that. You first you define like an envelope profile. It does not mean anything. All that it means is okay, depending on this envelope profile, whatever potential there is, whatever E naught I will calculate using this formula K naught plus P naught, that is going to give me my E naught value actually. So, that is the meaning of this envelope profile, and this was is selected for a different reason in a different problem actually. So, you can vary according to your wish, or you can simply fix a number also for that. This does not hurt actually. Then next you define a domain of interest, something like this, x of t y, such that x of t y norm has to be less than equal to some f envelope of f y. This is where the utility comes even more actually. Once you know this one, then these numbers can be selected in a good way. Okay. Now, this particular example, you take position thing has to be bounded by that kind of thing, as well as double spatial derivative is bounded by this double spatial derivative which is coming out of that, and these conditions also has to be 0 basically. Okay. Then here is the trick is we assume a Fourier series in this form, and then with this Fourier series this leads to this I mean if I compute this inner product, it turns out to be this expression, and by definition of our initial condition profile generation domain, this value, this inner product is less than certain maximum value which is a fixed number. That means this constraint equation has to be satisfied actually. Okay. Similarly, if you compute this inner product, this is actually the expression, and this has to be less than a fixed number which is also coming out of that, and these numbers have to be compatible. Remember that you cannot put arbitrary numbers just out of fun and all that way, and that is where this envelope profile helps us to get a compatible number set actually. Okay. Anyway, so getting that, so what is the idea here now in this particular case? We have to generate this a naught to a n, a naught, a1, a2 up to a n in such a way that these two inequalities have to be satisfied actually. Okay. Now, this represents, remember this value x max square turns out to be like this, and x dash norm max square turns out to be like this. So, satisfying these two inequalities, we have to generate numbers. Now, once you generate numbers satisfying some conditions like this, the finally remember we have to put it back in this formula, which will give us a smooth profile actually. Okay. So, that becomes much more meaningful actually. So, the algorithm sense let me not talk too much, it is available. I mean somebody interested can think a little bit and plug an algorithm there actually. Okay. Now, coming to the problem 1, which is actually nonlinear and linear heat conduction. The reason for taking this problem is like this. This is the initial stage of this development of this methodology, things like that. We wanted to have confidence on the problem, and we also wanted to have some sort of comparison study with respect to a known result sort of thing. And these known results that are typically available from operational theory, I mean infinite dimensional operator theory, but they are available only for linear systems actually. So, we went back to this one. Okay, this I mean this International Journal of Control and things like that. Okay, then you tell, I mean getting some inspiration from there and things like that. We wanted to experiment that actually. Okay. Alright, and also there are infinite dimensional distributed parameter system control theory books available, and that some results can be obtained from there actually, or at least for comparison sake. Now, the system dynamics is something like this. Okay. Very close to what you have seen before, but the fact that if you ignore this x minus xq term, it turns out to be the same problem what we started with this previous lecture very beginning slide, if you see that actually. So, this particular minus xq introducing this term makes the system dynamics nonlinear actually. Cost function is very similar to what we started again, this is a quadratic cost function, and boundary conditions are also similar, now both Neumann boundary conditions actually. Okay. So, if you ignore this term, okay, we have some way of comparing this thing with respect to the previous results that we already have using LQR theory essentially. If you ignore this term, we know how to kind of formulate an LQR theory in grid point sense actually. So, somewhere the results should lead us to the same value sort of thing. Okay. Alright, so going back to that, so this is what it is, the results turns out to be like that. You start with initial random numbers and all, finally it boils down to a kind of same value actually everywhere. Essentially this is a deviation problem, so everywhere everything has to go to 0. Remember this line represents the 0 line, okay. So every profile has to boil down to this particular line which is 0 actually, okay. Now that is what is happening. And associated control values also you can see, depending on the deviation it takes about the kind of opposite value of control and things like that, okay. And these are all with respect to the nonlinear problem actually, remember that. So we cannot have a real comparison study per se basically. So again a little more validation sort of thing from a sinusoidal profile, and it really even if it is a continuous profile, we are doing experiment with respect to the grid points values only. So we do not have any idea about what is happening in between really actually. But no matter, even if it is the initial condition which is sinusoidal, finally everything boils down to, everything decays out and it boils down to 0. Now somebody can argue that this is a dissipatory system anyway, that this system dynamics, okay, this is a stable term, stabilizing term, and this is also a dissipatory term. So that means this is stable dynamics anyway, so what is the big deal actually. Now if you really simulate this part of the system dynamics, well it will take you to 0, but it will take you in a different way. It will take some more time and things like that to take you to there actually. Okay, so like that. Okay. Alright, so more on that, I think this particular idea was not pursued too much heavily because there is no model reduction concept inside it, and hence it is not very elegant really actually, okay, because infinite dimensional theory has to have some sort of model reduction to make the system dynamics or the synthesis procedure more elegant actually, okay. But in fact somebody is interested in looking at more on that, you can read some of these journal papers, okay. And as I told, the very first paper happened to be in 2001 in Automatica, the next one in 2003 in Essence Journal of Control actually. So if you want to see some of these details, you can see that, okay. This is a conceptual paper, and this is actually a little bit realistic paper with some process control problem actually. Alright, now coming to the next idea, okay, this is where the model reduction concept is coming back, and here it is what we call as proper orthogonal decomposition, and using that will essentially, that is nothing to do with control design really. This will essentially give us some sort of a basis function using which we should be able to do a better job actually, okay. If you do not use that, you can still use Galerkin projection method and then use these generic basis functions, but that will again result in a large number of state variables actually, which you do not typically want it, okay. But on the other hand, this POD is not a miracle technique either actually, okay. Now if you ask me, this POD, the proper orthogonal decomposition ideas appear heavily in homogeneous system dynamic solution, and that is very much valid, very much justified, because the solution nature is not changing anything. There is no control input, so there is nothing like the solution behavior depends on the control input, there is no feedback there actually. That means every time you solve it from a different initial condition, the solution nature is sort of unique actually, depending on the situation, system dynamics. So those problems are okay. But when you talk about control in the loop, then we all know that open loop behavior and closed loop behavior are two different ball games altogether, okay. That means open loop behavior can be stable and closed loop behavior can be unstable, open loop behavior can be unstable, closed loop behavior can be stable, and much more beyond that actually, okay. So utilizing how do you generate the POD basis functions, because essentially you need some sort of a random representative solution profile to begin with, okay. But solution profiles itself are a function of control, and hence it is not available actually before synthesizing the control, and that becomes a kind of a loop, and hence people have kind of proposed something called re-POD and then online adaptive POD, all sort of things actually. Anyway, we will not talk too much on that. We will assume that the closed loop system dynamics behavior can somewhat be captured in the representative solution set, and hence utilizing their solution set we can generate a POD basis function set also basically. Alright, let us continue, get started. The motivation for that is first of all continuous nature of the state is accounted for, unlike the earlier design where only we bothered about discrete point behavior. The second one is it is a powerful model reduction technique, it leads to some sort of a very low dimensional system actually. And actually why this becomes low dimensional, because we do not deal with generic basis functions, we rather deal with problem oriented basis functions for control design actually. And that is the key reason why it becomes I mean why it results in low dimensional representation really. Then it can also be experimented with both continuous actuator as well as discrete actuators. We will not talk too much on discrete actuator in this class, but continuous actuators hence we will talk about, and then more on that you can read out and find out actually. The very first thing, as I told, is to start with some representative solutions which are called as snapshot solutions. Okay. So, this is the fundamental key things to design a good set of basis vectors actually, which and once you once you come up with this basis vector set properly, everything else turns out to be very good, and if that itself is not good, then everything else will turn out to be not good also. Okay. So, be careful about that when you talk about generating snapshot solutions actually. So, how do you do that? First you generate a state profile, okay. Then generate a random control profile. Now, when you talk about profiles here, remember these are distributed over space basically. Okay. So, generate some sort of a state profile as initial condition, and then generate some sort of a random control profile also as some sort of a control history basically. But remember, you cannot generate very randomly actually. Okay. But because if you really put a random control, then it may the system dynamics behavior can be very bad. It can even go to instability behavior, and you do not want that. Because with application of control, whatever dynamics it results in the closed loop, we want to mimic that in some sense actually. So, for that reason, we may use some sort of a stabilizing controller, or you can also use some sort of a logic actually to generate the state profile, and just hold it for some time. You do not allow it to go to keep on implementing for a long time and all that actually. That means, just to include a little bit of control excitation, you want to see that even if it is unstable, it may be still okay in some sense actually. And then utilizing this control simulate the system dynamics, okay, possibly using can use finite difference or finite element whatever it is, and then you can use then randomly sample it out of that. Okay. That means, this behavior which evolves with time, that also is a lot of lot of profiles actually. Okay. So, you do not want to keep on collecting everything, but randomly you select some profiles at different instants of time actually. Then you will have some sort of a snapshot solution using which you can actually design these basis functions well basically that way. Now, a small outline, again math details I will not touch it, but the small outline is like this. Once you have a set of snapshot solution, then you come here and tell, okay, ask this question actually, can I find a basis function phi in this way, where ui is nothing but the snapshot solution actually. So, that can I find phi as a linear combination of this snapshot solution, such that this function what you see here, integral value, that means the summation over this ui inner product phi and then absolute value square and then normalize of that actually. So, that represents the spread of this basis function really actually. Okay. So, if I talk about I got a basis function, then how well it can represent my solution set, that is captured by maximizing this cost function, again maximizing this, not minimizing actually. Okay. So, if you go through the algebra which is readily available in number of text papers and things like that, it turns out that it leads to some sort of a standard matrix eigenvalue problem, and this eigenvalue problem is nothing but that CW equal to lambda W. Okay. So, then if you have that kind of thing, obviously this is n number of eigenvalues and all that. So, find eigenvalues and eigenvectors accordingly, and that n will turn out to be the number of snapshot solutions actually, this n same n actually. Okay. But obviously you do not want that. If you want to retain everything, then there is no model reduction actually. So, it turns out that the very first eigenvalues after ordering and all, if you find the eigenvalues and then order them, because this happens to be a symmetric matrix, it will all happen to be kind of real eigenvalues and all that. So, you can order them, and it turns out that very quickly this eigenvalue set will converge in this sense. That means, if you start summing up lambda 1 plus lambda 2 lambda 3 lambda 4, then probably even if you sum for up to 100, then it does not matter, it will be still approximately same, and is very quickly it will converge to that summation actually. Okay. In other words, the total spread of the basis function set is contained within some first couple of basis functions really actually. And pictorially you can see that way. In this particular problem, if you take just 5 basis functions, it will, so first one will contain 65%, first two will contain about 92% 92%, first 3 will contain about 98%, like that actually, 97%, 97.5 like that. And then if you just take about 5 basis functions, you are done. Even if you have collected some 200 snapshot solutions to begin with, we will ultimately end up with this 5 basis function vector, and hence a 5 dimensional representation of the lump parameter system. That is that powerful actually. It again, it depends on the solution. I mean, that depends on the representation of the solution through snapshot. That is again the key. What it tells you is capturing the behavior that is captured in the snapshot solution. Now the question is whether the snapshot solution really behave, I mean, close to the closed loop behavior of the system dynamics or not. That is up to us to decide, judge or guess or things like that actually. If it is close to that, this truncation will happen even very quickly actually. Okay. That means we are done actually. But this picture tells you everything. Even though we started with 200 snapshot solution, ultimately 5 basis functions it results into because of this behavior, okay, this lambda convergence behavior, and hence the number of basis, I mean the dimension of the lump parameter system happens to be just 5 actually. Okay. Then after you get the basis function, finally you have to go through some order reduction procedure. In other words, from PD to ODE you have to get it using these basis functions and all that. So generic sense it becomes mathematically complex and all. I'll kind of demonstrate that using a simple example actually. So we'll go back to the same equation, linear heat equation with Neumann boundary condition, okay, that we started with this first example problem of the previous lecture. So this is where the fundamental understanding happens actually. So we start with this simple linear PD with Neumann boundary condition. And when you talk about inner product definition in everything, what you talk here in continuous time, I mean continuous space is something like this. When inner product of phi and psi is just pi and psi multiplication and integrate over the domain actually. Okay, that is the definition of inner product. Then here we assume a continuous control. That means this state and this control we expand in this form. This is model form representation. Now these phi's are basis functions that is available through this analysis and all that, whatever. Okay, this solution set and all that will give us something there. But anyway, so coming back to that, this is once you have the set of basis functions, this phi 1 to n, and this case 1 to phi basically. Okay, so x is the state vector is expanded as function of purely a function of time times purely a function of space. This is the separation of variable sort of ideas actually. Similarly, control is purely a function of time and purely a function of space. Now this function of space is already computed because of this orthogonal basis function and all. What remains to be computed is something like u hat of and x hat. That means x given an x of t y, we should be able to find out what is x I hat of t at every I, and then based on that we should be able to compute this u I hat, and based on that we have to get a continuous controller actually. That is the whole idea there. Okay. Alright, so how do you do that? First of all, we have this system dynamics. So and this expansion actually. So this expansion we can put it back here, okay, and then this will result in that sort of representation. Now you talk about inner product with respect to phi j. Okay. So if you do inner product with respect to phi j, remember these are all orthogonal basis functions actually. That means unless I equal to j, the inner product is 0, and if I equal to j, this is I mean this is normalized sort of thing actually, but typically this is sometimes 1 if it is normalized already, or otherwise particular value actually. Okay. So this represents inner product. Let us say it is okay. Let me talk about that. Okay. These are orthonormal basis functions, not necessarily orthogonal. So the orthonormal means if inner product phi I and phi j happens to be 0 unless I equal to j, and if I equal to j, this is 1 actually. So utilizing that behavior here, okay, and noting that summation, this partial derivative, everything is inner product also, these are all linear operators. You can carry out the algebra and ultimately it results in some sort of equations like this. Okay, and these are numbers, remember that. This is not, see, the basis functions themselves are orthogonal, but once you take special derivatives and then take inner product, they are not orthogonal actually. So you have to really compute it numerically using let us say trapezoidal rule and things like that. So, these cannot be represented through delta function and all that actually. So, this has to be evaluated explicitly. Similarly, this also has to be evaluated explicitly. But nonetheless, I mean if you think about doing that, okay, this one either this or that, it can be actually evaluated explicitly. That's not much of a big deal actually. Okay. Now, it will ultimately result in a finite dimensional system, and that finite dimensional system will tell us that this is the form where x hat of dot is a x hat plus b u hat, where this A matrix, the component of A I j can be computed that way, and B happens to be identity actually. So, ultimately we got a representation in the finite dimensional space, lumped parameter representation really, but this x hat do not represent any grid point solution. Okay. These components of x hat, which is x 1 hat, x 2 hat and things like that, they will go and sit here actually, and once everything is known, once you put it back in this formula, then you will get x of t y really, and similarly for the control. But individually they represents the magnitude with that will go along with that basis vector, okay, basis function really. Okay. So, that is the meaning of this time varying numbers basically. Okay. And this is the meaning. If you really want to extract this x I hat, which is a function of time, then again utilizing this orthonormality behavior and all, it turns out that inner product of this and that is nothing but that, and inner product of u and phi j is nothing but u hat j basically. So, given an x, you first compute through this inner product this fellow. Now, our job is to somehow connect these two. Okay, these are time domain behavior actually. Okay. So, once you know this, we have to find out this, and once you know that, we go back and tell, okay, I got my control throughout actually. Okay. That is the whole idea there. So, given a nonlinear problem, again it will result to a similar sort of things, but there will be an extra term here. Okay. This extra term will be something like this actually, because of this minus x cube, we will have an additional nonlinear term, which nonlinear term turns out to be something like this. Okay. By the way, this problem has also been solved using this theta d method and all that. Those of you are interested, you can see that in one of our publications in optimal control applications and methods actually. So, that is a different approach altogether. But here we are talking about solving it using SNSE actually, so single network adaptive critique. Okay. So, the cost function is again like this, but we have to have a representative cost function in the time domain. So, again this one is nothing but inner product of x and x, this is inner product of u and u. So, again substitute the expansion actually, x is nothing but the expanded by like this, and again same thing, and then u is something like that and things like that, and you expand it this summation and that summation and put it together, excite the orthonormality behavior again, and it turns out that is not difficult at all. J turns out to be something like this, where q is nothing but q times I and r is nothing but r times I. So, this J what you see here and this system dynamics what you see here, they represent some sort of a regulator problem, but it is a nonlinear regulator problem. And also because this is control affine to begin with the PDE, it also results in some sort of a control affine nonlinear system dynamics. So, obviously, when you have a control affine nonlinear system dynamics and then you have a quadratic cost function, okay, you can excite this idea of adaptive critique or single network adaptive critique like that and get better solutions actually. Okay. All right. So, now how do you get the results like this? How do the results look like? Something like this. We have a sinusoidal initial condition. And use, okay, I am not talking too much details of after this, because we know this is a compatible set of cost function in lump parameter, and this is a system dynamics that goes along with that. We have also talked about how do you generate random initial conditions and all that little before using 2-3 different ideas, and after you generate, how do you come up with this coefficient values, time varying coefficient value, that also we discussed actually. So, Pitts and Pitts components we have discussed already, and SNSE we know how to synthesize it. So, I am not talking that particular architecture in detail again. How does the results look like? Results are something like this. You have a sinusoidal initial profile, everything turns out to be 0 very quickly. Control also goes to 0 simultaneously actually. Okay. Now, what about this state and control of nonlinear problem from a different initial condition including constant, it again goes to 0, and here control also goes to 0. And what about this? Some sort of a random curve profile, okay, and you tested many number of times. Initial profile is very arbitrary here, but what smooth, okay. So that one, if it is there, then something like this, okay, which all happens nicely, okay. Again, now we come back to the linear problem, and then you want to have some sort of a comparison with results. Okay, these results are taken from a textbook of infinite dimensional operator theory based quadratic regulator design and all that. So, this problem has been solved there, and using that solution, whatever is proposed there in that particular book, we talk about utilizing this actually. Okay. So, this is the SNSE solution, okay, and this is the closed form solution. Visually you can see very close, but error also you can plot and see error values are very small, and it ultimately goes to 0 everywhere actually. Similarly, you can see this from a different initial profile, again visually they are same, error sense also they go to very small value, 0 basically ultimately. So, these are comparison results which will guarantee that things are happening in a good way basically. Again from a different initial condition, sinusoidal profile where looks very similar, error also 10 to the power minus 3 here, remove that, these numbers are 0.4 and all that, and in that sense, but finally it's very close to 0 basically. Okay. This line is 0 line actually, you can see that it's almost approaching that actually. Alright, so these are confidence building exercises actually. Okay. Then another one, comparison of control linear problem, sinusoidal initial profile, you have a control comparison here, okay, and then even though because this control, okay, this control is not same as that control, obviously not expected to be. This control is very good because the moment it sees some sort of a constant profile, the closed form formula that will automatically do a lot of good things there actually, because it does not approximate anything to begin with actually. But here we always work with an approximate system dynamics. So, there will be some small deviation initially, but ultimately in asymptotic sense very quickly they all go nicely, and then that way it is not bad actually. And even if there is a variation, the variation is not really very bad. Now, if you see this variation, what you see is 0.2 here is almost 0.2 with a little bit plus, I mean more than little bit lesser than minus 0.2, and sometimes little bit small and things like that, but on and around minus 0.2, okay, the value average value sense it will turn out to be very close to minus 0.2 only. Error sense, this is what it is, error things are happening, but very quickly around that time, very quickly the errors are all converging to 0 basically. Alright, so about 2 seconds of operation, it turns out 2 or maybe 3 seconds of operation, errors are gone actually. Now, this idea, okay, both these ideas have been also experimentally validated, it is just not math actually. So, this experimental validation setting also gives us a little more confidence of the ideas that have been proposed and all that actually. So, this little details on that you can look at this conference paper if you are interested in, but I mean the first problem in any experimental validation turns out to be the modeling accuracy. Okay. What we conveniently assumed as alpha is equal to 1, beta equal to 1 in our all math analysis is not true. And in general, it turns out that alpha beta are not even constant, they are actually functions of y. So, this system identification is first thing to do, and that itself was a procedure actually. Okay. We had to do several experiments and then things like that. And one of my colleagues, this Swayam Prabha, who was a master student actually, he did lot of these experiments himself, and then we had this collaboration thing actually. So, this alpha and beta, okay, those have to be identified from experiment first, and that was carried out first thing. Okay. That I will not talk too much details on that of course. And this was the experimental setup. You have this because experimentally you cannot talk about continuous sensors and things like that. So, we have this layers of sensor actuator things like that, and layers of these aluminum slabs which are set up like this. And also remember, our boundary condition tells that they have to be insulated at both ends. So, both ends have to be insulated, and some degree of precaution was actually taken for that also, okay, both ends. And then they have to be skewed away, that means some sensor and actuator they cannot be on the same row sort of thing, then it may pick up some wrong values and all that actually. So, sometimes you skew it away from that, so that okay, there is some degree of reliability and things like that of the numbers. but truly I mean this the one dimensional representation that we are talking about doesn't hold good really. This is a cylindrical problem, and hence there is a radial dissipation of energy also, not just axial, and that is the whole problem actually. I mean here we are assuming that all slabs will attain equal temperature throughout immediately actually, which is not really true, but despite that the results are very encouraging actually. All right. So this is what you see there actually. All right. So this is the schematic of this. You have this 11 thermocouples and things like that. You have the aluminum slab. You have taken a one dimensional heat conduction modeling sort of thing, and there were 10 heaters, okay, like that. And there are some hardware settings, and then this conceptually like this. You have a kind of experimental setup where you have to measure the temperature, and there has to be some sort of a, I mean, external multiplexer sort of thing. Then you pass it through this implementation through LabVIEW, and that time it was Pentium PC actually, and then some digital IOs, and then the control input was given to the experimental setup actually. Alright, so the implementation issues were several things. First thing is closed loop state feedback control. So how to relate training range of neurocontrol to physical temperature readings actually. So that was an issue. So use normalized data as input to the neurocontrol. Okay, that was some sort of a solution that was proposed. Okay, use normalized data as input to the neurocontrol, that solves it. The neurocontrol needs understanding of all weight connections in the network, and each node has one controller. So total something like 648 weights, and biases has to be handled using LabVIEW, and that time it was manual coding in LabVIEW. So LabVIEW take and manually you code these numbers, so 648 numbers, and each of the number will have some large number of digits after point also. So faithfully you have to code it manually basically at that point of time. Now it may not be done because there are some automatic procedures available and things like that. Alright, so now the question is how to get temperature values at heater locations, okay, because you are assuming also there is something called collocated, non-collocated and things like that. When you have I mean all throughout you have been assuming collocated action, that means where you are applying control, exactly there itself you are measuring the input, I mean measuring the output, and typically that is not feasible, okay. So non-collocated implementation is typically advisable in distributed parameter system, because it's the exactly same point you cannot take a measurement actually, okay. So then how to get the temperature values at a heater location? Those are like practical implementation issues really. And there are also issues in a control implementation sense, because you can always give heat input, you can heat it up, but when necessary you cannot cool it down. There was no cooling mechanism really actually. And also there is something like, okay, if you want something like 50% of the flux load, that means total something is some maximum excitation is there, or so let us say you want 50%, then how do you implement? It may not be feasible also that sense. So in a way, in a different way it was done, it was some cycle time is there, and then if you really want 50%, then only up to 50% it was made on actually, then rest of the time it was left free. Then obviously all these approximations that you do as part of the experiment also degrades the system dynamics behavior, the assumptions that we rely on in the theory actually, okay. So you don't expect too much of neat results actually in that sense, but despite all that the results were very encouraging actually. Alright, so this is in summary, this is this experimental setup. There was some data communication and things like that, and ultimately there was a multiplexer through which I mean this this was connected to the PC and sort of like that. There is a power supply which is connected. I mean this is very standard thing actually, okay. And then this is a system that is ultimately where experiments keep on going actually, okay. And again that was a Pentium PC through which the commands were given and the sensor values were read and all that actually. This is the final result. I mean ultimately we wanted to have uniform temperature and all that. So very end at the boundary it was not able to do a very good job. Obviously there is insulation problem and implementation issue and all that, but nonetheless it was able to control in a very good way. It was coming to the all constant values irrespective of where you start actually, okay. So if you really want a constant profile, roughly it is doing the job actually. So if you really want a sinusoidal condition, remember this is not a constant thing, this is a slight slight sinusoidal behavior actually, okay. Just look at the star things and can try to connect. This is actually kind of a sinusoidal thing. Even if you want that, it was happening actually, okay. So, all that things that these are nice things which gives us a lot of confidence that experimental validation also it can happen actually. So, summary of this entire control design approach using this POD and Galerkin representation, things like that. First of all, it results in a very low dimensional system of ODs. Again, this entire way of mechanizing or handling this PDE systems is somehow we have to have some representation of ODE and then excite this ODE control design philosophies and things like that. One way is to don't bother about model reduction and then simply go ahead and implement in finite difference. And also, let me put a comment here that even if you do that, the finite difference once you implement it, then utilizing that large dimensional system, there are some model reduction techniques available also. So, that way also you can reduce the model. You will generate a large dimensional representation, then you excite these eigenvector concepts and all that, and then finally you will reduce the system dynamics there itself. That is also a possibility to look into. Another representation the people have also thought about why finite difference all the time. I can actually talk about finite element, finite volume and things like that actually. So, if you incorporate those things, then not only I am getting some grid point values, but I also get some numbers in between the grid points actually. Okay. So, those things are also possible once you use this finite element and then finite volume approaches like that actually. Alright, so this exercise, this opens up a lot of different dimensions. Depending on your comfort zone, you can explore whatever you want actually. Also, these are very relevant to this chemical industry problem, same of that actually. So, process control people, if you are happen to go through this lecture actually, you may find it very useful really actually. Anyway, coming back, the lesser number of neural networks, it will result because there is a low dimensional representation. It will also result in lesser number of neural networks actually, and hence in a way it will result in structural and computational simplicity basically. Okay. And it is possible to synthesize both for continuous actuator as well as set of discrete actuators. And discrete actuator things I have not talked about here, but somebody interested you can read one of our publications actually. Okay. And then we got a lot of promising results and then successful demonstration through experiment also. Then various other problems were solved. For example, it was some ecology problems, some beaver management issues in the jungle and all that. You have done it. It's just for fun. And then this is not one dimensional PD, but it has two dimensional PD. That means two spatial variables y1 and y2, because the animals will spread in different directions in jungle actually. So, one direction itself is not sufficient to handle that, but essentially the idea remains same and the tricks and techniques remain same actually. So, no matter whether one dimensional OD or one dimensional PD or one dimensional means one spatial dimension essentially. So, whether it is one spatial dimensional PD or 2 or 3 or 4, it does not really matter, because the basis functions take the load. And once you introduce this separation of variable concept sort of thing, the time domain, the time evolution behavior is captured through the coefficients actually. So, because of that the generality is maintained actually here, and hence we can actually do many things there actually. Okay. But obviously, the math complexity and computational complexity it tries to pile up, because in one sense you talk about single integration. Now, if it is 2D two spatial variables for evaluating the inner product, you will have to have double integral sort of thing, two dimensional integral sort of thing actually. So, then this math and computational complexity will creep in really. Okay. But in general, in my view, POD happens to be a good thing, good approach. However, as I told you in the beginning, that POD all relies on the snapshot solutions. So, that is the bottom line. So, now going back and thinking a little bit, snapshot the solution is good, the procedure is good as long as the snapshot solution is good. Now, how do you generate a good set of snapshot solution? That again depends on the intuition, depends on the prior experience, depends on several ad hoc procedures. And then, as I told before, the people have proposed a different way of doing things, something like adaptive POD and then dynamically reoptimization of PODs and things like that actually. That means you do not generate the basis functions once and then keep on working on that. You can have a procedure where the basis functions themselves get refined and as you go along actually, okay, because you will have better and better snapshot solutions as you go along actually. So, those kind of ideas are available in the literature. You are most welcome and encouraged to read all of that and then build further actually. It is a fascinating area of research in my view, and there are a lot of practical significance in general as well actually. Alright, so with that I will stop this lecture. Thank you.